Good afternoon. Myself, Samir Mondal, a Prime Minister Research Fellow in the discipline of mathematics at IIT Madras. This is my tutorial for live sessions. Okay. In this session, we'll discuss about extreme value of two variable functions. Okay. So before going for two variable, we want to discuss for single variable functions. Then we'll generalize this concept for two variable functions. Okay. So what do we mean by local maxima, local minima for single variable functions? Okay. So today our discussion topic is extremum value. Extreme value. Okay, this is our topic of discussion is extremum value for two variable function. Okay, so before going to two variable functions, at first we will discuss about for single variable function. What do you mean by local minima, local maxima, global minima, global maxima? Okay, and what is the extreme value? First we will discuss about single variable functions. Suppose you have one function from domain which is a subset of R to R. This function is your given. Okay. So what do we mean by local maxima, local minima? First we will discuss about local maxima. Okay. So this is your function is given. Okay. If function has a local maxima, okay, at a point A, okay, if f of x less equal to f of a, okay, for all x near or we can write like that, for all x near to A. So what do you mean by near to A? Okay, why we are using this term? Okay, so basically this term is represented at neighborhood of A, means f of x less equal to f of a for all x belongs to neighborhood of A. This line is imply for all x belongs to neighborhood of A. This near is represented by the neighborhood of A. Okay, it's fine. So we can draw a picture geometrically. We can observe it. Suppose you have one functions like that. Okay, and this is your domain. Okay, so what is the local maxima? You can observe that this is your maximum point. Take this is your A. Okay, so from here we can observe that take this one neighborhood of this point A. Okay, this is your neighborhood of A. So in this neighborhood f of x is less equal to f of a. for all x belongs to, give the name of I. For all x belongs to I. So when we are taking one neighborhood of A, we can observe that f of x, all functional value near about this point f of A are less equal to this value. Okay, so this is your local maxima, okay, at the point A. Okay, so graphically we can observe one thing, that suppose when we are talking about local maxima, okay, we can observe that this function, suppose this is your point A, okay, this is your point f of A. We can observe that this is your what? This is your local maxima at a point A. So when one functional value, okay, when functional value at a something point A is a local maxima, that time we can observe that from left side the function is increasing. Okay, from your left side of A, your function is increasing, and your right side of this, okay, this is your decreasing. So from graphically we can observe these things. Okay, let write down that things. Here we can note one things. Note yeah, basically today we are discuss about extreme value for two variable functions. So initially we are restriction as for single variable functions. Okay, so what do you mean by local maxima for a single variable functions? A function defined on a domain D, which is a subset of R. A function f has a local maxima at a point A if f of x less equal to f of A for all x near to A. What do you mean near? What do you mean by this term near? This near is nothing but a neighborhood of A. Okay, so near means, near to A means we are taking one neighborhood of A. So in the neighborhood, if one function satisfies this inequality, okay, then we will say that at the point A, f has the local maxima. From the graph you can observe this properly. Okay, so this is your this is your local maxima. So for this value f of A, okay, at the point A we can observe that f of x less equal to f of A for all x belongs to I. Here I is this open interval, neighborhood of A, this is your I. So we can observe these things from graphically. Okay, and another one things also we can observe, such that this is your local maxima. Okay, so that time also we can observe that when we are going to from these directions, okay, your functional value is increasing. When we are going for this direction, your functional value is decreasing. So this is the one property of functions have to satisfy for a local maxima. Okay, the graph, so here I am writing down that one. Okay, the graph of a function y equal to f of x has a local maxima at a point where the graph changes from increasing to decreasing. Okay, so suppose this is one thing. Here you have local maxima. Okay, so from this picture we can observe that the graph of a function y equal to f of x has a local maxima at the point where the graph changes from increasing to decreasing. So from here graph is in this portion graph is increasing, in this portion graph is your decreasing. So the graph of function y equal to f of x has a local maxima at a point where the graph changes from increasing to decreasing. So using this node we can observe that this is your local maximum. Okay, and another thing also one can observe, we can, if you draw a one tangent here, okay, we can observe that the at this point tangent has the zero slope. Okay, one can also observe that at this point tangent has zero slope. Okay, where tangent has zero slope, where the graph changes from increasing to decreasing, at that point tangent has the zero slope. Okay, so similarly one can define the local minima. Okay, one can define the so for local minima we will replace less equal to sign. So similarly one can define the local minima. So here what we'll do, we'll replace less equal to sign by greater equal to sign. Okay, so for your local maxima it was that f of x was less equal to f of a for all x belongs to neighborhood of a. So for minima we'll replace this less equal to sign by greater equal to sign, means for all functional value, okay, at the neighborhood of a should be greater equal to that functional value at the point a. Okay, that time we'll say that f has a local minima at that point. So graphically we can observe this one. So we can observe that at this point f of x is greater equal to f of a for all x belongs to neighborhood of a. Okay, and another things also we can observe here, your from that side your function is decreasing and from this side your function is increasing. Okay, or we can tell like that, sorry, if your origin is here, okay, if your origin is here, so we can tell like that from this side your function is decreasing and from this side your functional value is increasing. So graphically we can observe these things, that graph has a local minima. Okay, so the graph has a local minimum at the point, okay, at the point where the graph where the graph changes from decreasing to increasing. Okay, yeah. So from this graph we can observe that at this point your function has the local minima. So at this point graph is changing from decreasing to increasing. Okay, so graphically you can say like that. And another things also we can observe that at this point if you draw one tangent, okay, if you draw one tangent at this point, slope of this tangent is also 0. Okay, so at the local maxima and at the point of local minima, the slope of the tangent at that point is 0. Till now is fine. Do you have any question?
No, sir, clear.
Thank you. Okay, at this point the tangent has 0 slope. Okay, so till now we are discussing for local maxima, local minima for a single variable functions. So now we are interested to extend this notion of local maxima and local minima to a function of two variable. Okay, so till now we are discussing for single variable functions. Now we want to extend our this concept for two variable functions. So now I want to recall once again. So for local maxima, okay, so a function f has local maxima at a point a if f of x less equal to f of a, okay, here for all x in neighborhood of a. Okay, so this concept will extend for two variable functions. Okay, so now your function f will define in D. D is a subset of R2 to R. So your f is a function of two variable. Okay, here f has two independent variable. Okay, take AB interior point of D. Okay, so now we will define the local maxima. So when we will say that f has local maxima at the point AB, when we will say we will say that we say that f of xy has a local maxima at the point AB if f of xy less equal to your f of AB for all xy belongs to D and near to your AB. So what do we mean by near? So this inequality will satisfy not for whole domain D, only the near to AB. Okay, so what do we mean near? Near is nothing but a neighborhood of AB. So here we are referring this near term as a neighborhood of AB. Okay, not for all x, y and d, only one particular neighborhood, not particular, one small neighborhood of AB. Okay, it's fine. So that time we will say that f of xy has a local maxima at the point AB. Okay, it's
Oh.
fine. It's fine.
Yes, sir.
And this near term we can remove and we can write like that. We can someone can write like that. Is meaning like that. That is, for all xy in some appendix. Okay, center at AB and contained in your D. In this appendix, if one function satisfies this inequality f of xy is equal to f of AB, then we will say that f has a local maxima at the point AB. Okay, so suppose this is your region D. Okay, this is your point AB. So only we will look at one appendix of AB. In this appendix, okay, you have to satisfy, the function have to satisfy this inequality. Then we will say that f of xy has a local maxima at the point AB. For all x, y, suppose take this appendix name as I. For all x belongs to I. It's fine. It's fine. Is it clear for what is the local maxima?
Yes, sir.
Okay, thank you. And the number f of AB is then called a local maximum. Okay, local maximum value of f of xy. Okay, and the point is called a point of local maximum of f of xy. Okay, so till now we are discussing about for local maximum and local minimum. Okay, so initially we was discuss about for local maximum for single variable function. So here we can observe that local maxima and local minima is what? It's not a global property, only local property, means is depend on only neighborhood of that point. Okay, we'll check the inequality on the neighborhood of that point only. So global means we have to check for whole region. Okay, so when we are talking about local maxima, that time we will check about only on neighborhood of A for single variable, and for two variable function we will check one appendix or open neighborhood of AB. Okay, that inequality, that if that inequality is satisfied, then we will say that if for single variable f has a local maxima at the point A, and for two variable that local maxima at the point AB. So this is only the local property. Local property means depend on the neighborhood of that point. Okay, so when we are talking about for global maxima, global minima, that time this inequality you have to, that function have to satisfy for whole region. Okay, is it clear? So I can give you one example. Okay, that global maxima and global minima and global maxima and local maxima is not same. Can you give one example? Could you please give some example? So we can observe like that. Suppose I'm giving an example for single variable functions. Okay, where your local maxima and global maxima is not same. Okay, take this function. Okay, here you can observe that this function is increasing, after that this is going to decreasing. Okay, so if you take one neighborhood of that point, take this is a, if you take neighborhood of that point, okay, your function will satisfy the inequality f of x less equal to f of a for all x belongs to neighborhood of a. Is it or not? So at the point this one, your function f has the local maxima, local maximum. Okay, but f of a is not the highest value of f, because you can observe that this point is the highest value for the domain. Okay, suppose this is your domain, full domain, this one is D. Okay, so this f of a is not the greatest value of f in D. So A is a local maximum point, okay, but not a global maximum point. Okay, is it clear? So this is your global maximum point. Okay, is it clear or not? Please tell me.
Yes, sir.
Okay, so the same concept we can define for two variable function. That time you can also call is global, or we can I am using one different name for two variable functions. You can also use that one. Absolute maxima, we'll use absolute maxima. Okay, absolute maxima. Okay, so suppose you have one two variable functions defined on a domain D, which is subset of R2 to R. Okay, we'll say that f has absolute maxima at a point AB from D if f of functional value in one open disk of AB is less equal to f of AB. That time we'll say the local, but this time we have to satisfy for full domain D. Okay, means we say that f has an absolute maximum at AB belongs to D if for all xy belongs to D, your functional value have to satisfy this inequality. Here for all x belongs to D. Okay, so in full region your f of AB have to be the greatest value, greatest functional value. Okay, it's fine. For local maxima we will check only neighborhood of AB, neighborhood of that point, and for global or absolute maxima we will check in full region. Okay,
Okay, sir.
yeah, thank you, it's fine. And that point AB will call as a point of local maximum. Okay, sorry, we can local one is point.
Sir?
Please tell.
Sir, can you explain local maximum in 2D in terms of contour plots?
In term of
Contour plots, sir.
contour close means I don't know. Please, could you please explain?
Sir, contour plots.
Please tell me what is this. I couldn't understand. Contour clause means in terms of the theorem or something. I couldn't understand. Could you please explain what is this?
Okay, sir, I will explain in just a minute. Okay, wait.
Yeah. Contour plot. I don't have idea. We will discuss in after of this class. Is it will be okay for you? Azhar?
Okay, sir, no problem.
Yeah. So at first I am finishing this lecture. Then we will discuss on this topic. Okay. So
Fine, sir.
yeah. So this AB is called the point of absolute maxima. Okay, and that functional value f of AB is called absolute maximum value. Okay, so this concept we can same definition we can use for absolute minimum also. That time we will replace that less equal to sign by greater equal to sign. Okay, so when we'll say that one function has the absolute minima, that time we'll say that f of xy greater equal to f of AB for all xy belongs to the domain D. Okay, so we can generalize this concept. We can same definition we can use for similar definition we can use for your absolute minima, and we will replace the less equal to sign by greater equal to sign. Okay, now the next question is it possible to check that f of xy is less equal to f of AB, and is it easy to find that point AB? This is a question. How will find that point AB? Okay, or is it easy to find, or is there any technical tool that we can find that point AB? Okay, when we are talking about definition is very interesting, is fine, but we have to find the point AB and functional value at the point. Okay, AB. So is there any tool? Do you know any idea how to calculate this point AB? Azak, do you have
Sir,
any idea?
differentiation?
Differentiation of, okay, for one variable we already know that when your extreme value exists, at that point that derivative of that function at that point have to be 0. Okay, that point we will say that extremum exists. Okay, after
Yes.
that we will go for second derivative. We will check the sign of second derivative at that point. Okay, and we will talk about maximum minima. So is there any theorem or something for two variable function? Do you know?
No, sir, no idea.
Okay, so I am explaining. Okay, what is my, yeah. So, and before going that, I am mentioning another things. This is combined of local maxima, local minima, local extrema. Okay, this is local extrema. Local extrema means either f has local maxima or f has local minima. This is the called the extremum. Okay, either f has two local maxima or local minima, one of that time we will say that f has a local extremum. Okay, at the some point.
Okay, sir.
Okay, either local maxima, local minima. It's very simple. One note one things, when we are talking about local, that time we are talking about interior point of D. Do you know about interior point? Suppose I am giving one dix. Yeah. What is the interior point of that one? This is dix. Do you know what the interior point of this one?
No, sir.
Okay, so I'm not going the deep definition. Only you can I'll tell one simpler things. This is your dix. Okay, interior point of this dix is nothing but we'll remove that boundary point. We'll remove boundary point. Okay, and we'll collect the all point in inside. This is the interior point of the dix. Okay, suppose you have one region like that, full region. So what is the interior point of this region? We will remove only the, what will remove? We will remove only this one.
Boundary point, sir.
Yeah, we will remove only boundary point. This one we will remove. Okay, then we will get, this is approximate, yeah, concept of interior point. There is topological definition is there. I am not going for those things. Okay,
Got it, sir.
yeah. So one note is that for local extremum, point must be an interior point. Okay, so note that. Notice that a local extremum point, okay, must be an interior point. This is clear or not? Please tell me. Local extrema point must be an interior point, because for local extrema means local maxima, local minima, we are talking about or neighborhood of that point, means one open dix of that point. Okay, suppose this is your region, suppose. Okay, so if open dix means like this one things. Okay, suppose this is your AB. So that time we are talking about that inequality satisfy only in this region. But if suppose this is your AB point, that time we will not get any open dix. That must be contained in region. But here the open dix is going to outside. Is it or not?
Yes, sir.
Yeah. So when we are talking about local extrema, your point must be an interior point. Okay.
Okay, sir.
But whereas an absolute extremum point need not be an interior point. Okay, because that time we are talking about full domain D. Okay, not about only open dix. That time we are talking about full domain D. So for your absolute extremum need not be interior point. So when someone are going for find the local maxima, local minima, that time if someone only look for the interior point, that is enough. But for when we are look for absolute extremum, okay, that time we have to look interior point as well as boundary point. Is it fine?
Oh, okay, sir.
Yeah. So now we'll go for how we can find that local maxima, local minima. Okay. So before going that, so in your here we can observe one thing, that for your local maxima, local minima, that when your functional value changes from increasing to decreasing, that point your function has local maximum. Okay. At that point if you draw one tangent, tangent has the slope 0, means your first derivative at the point f is 0 for single variable. Okay, so this concept we can apply for your second variable also. That point will call critical point. So what is the critical point? Critical point. Okay, and interior point AB, okay, of D. We are taking one interior point AB of D. Okay,
Okay, sir.
is a critical point, okay, of f of xy if either your partial derivative with respect to x at the point AB is 0 and partial derivative with respect to y at the point AB is 0, or either these have to satisfy, okay, or at least one of this one does not exist. Okay, either f has to satisfy this condition, that partial derivative with respect to x at the point AB equal to 0 and partial derivative with respect to y at the point AB is 0. Either that function f have to satisfy this condition, okay, or at least one of this one and this one does not exist. That time we will say that point AB is a critical point of f of xy. Okay, this is the one definition, basic definition. Okay, so one theorem is there. Suppose this is your critical point for your two variable function f. Okay, suppose this is your collection of all critical point. One theorem is there, extremum value, okay, so not extremum value, the point of absolute extremum or point of extremum, you can tell, or local or minimum, whatever. So point of extremum is a subset of this one. Understood what this theorem says?
Sir, can you explain it again?
Okay, so this is your collection of critical point. Okay, this is your collection of critical point of the function f. Okay, so that time your point of local extremum, okay, local extremum points, okay, suppose this is your local extremum point, suppose this one, okay, and this is your collection of all critical point. That time local extremum point is a subset of critical point. Okay.
So, sir, that means local extremum points are the subset of critical points.
Yes.
Okay, sir.
Yeah, one theorem is there. I am writing that theorem. Okay. Theorem is like that. So one two variable function is defined on a domain D. Okay. Subset of R2 to R. This is your function is given already. Okay. Take AB. Okay. Be an interior point. Here we are talking about local only, local extremum. Okay. So take AB be an interior point of D. Okay. If f of xy has a local extremum at AB, okay, then AB is a critical point of f of xy. Okay. So
Okay, sir.
yeah, I'm taking one interior point from D. If f of xy has a local extremum point at the point AB, that time that point is belong to the critical point of AB of f of xy. This is the picture. This is your this full design is collection of all critical point of A, and this red region is collection of all local extremum points. So local extremum point is subset of your critical points for a given function. Okay, till now it's fine.
Yes, sir. Clear.
So now little bit easy. So till before that before this theorem, there is no tool or something for find that what what would be the your possible local extremum value or sorry, local extremum point. Okay. So before that theorem, there was not any tool. So what would be the your possible AB such that it at that point if your f has local maximum local minimum. But this theorem says that if you find the at first if you find a critical point, so this is the bigger set of your local extrema. So if you are if you are able to find the critical point, then your work will be very easy. After that few steps will be there. Suppose you are getting total 5 critical point. So among these 5 critical point, maybe 5 are local extrema, maybe 2 or 3. So in domain there was uncountable many number was there. From there we are looking for only few number right now. So because critical point is very easy to find, you have to find your partial derivative with respect to x at the point AB. You have to equal to 0, and partial derivative with respect to y at the point AB. You have to equal to 0, and you have to find x and y. Okay. So
Okay, sir.
yeah. So now it's little bit easy to find that AB. Okay. After that you have to check is it local maxima or local minima. This is enough. Okay. So here we can see that this is okay. I am removing this little draw line. Okay. Yeah. So this is your collection of full critical point, and this portion is your local extrema point. So what are these things? Okay. What are these points? So in your this subset, when your local have the local extremum, that time we can compare between either f of x less equal to f of e or greater equal to. Extremum means either local or minimum. So in that point we can compare the functional value either less equal to or greater equal to. But in those point we can't compare. Means suppose take one value we have. Okay, take this is a CD. Okay. Okay.
Yes, sir.
Yeah, that time we will get one pair x1 y1 and another pair x2 y2, such that this will be happen like that. So properly we can tell that all functional values less equal to this one, we can tell like that for all this point. But from this point we can tell that, and on some neighborhood the functional value is less equal to that f of ab, or the functional value is greater equal to f of ab on some neighborhood. But for those point we can say like that. Okay, we will get some neighborhood, some close point x1 y1 x2 y2 of cb, such that this will be happen for those point. Is it clear or not? Please tell me at first.
Sir, not clear.
Okay, okay, I understood. Okay, okay, I am taking properly. Okay. This is your critical point. Okay, this is your local extremum point. Okay, so in local extremum point choose one point ab. This is belongs to your local extremum point. Local extremum point. Okay.
Okay,
So
sir.
local extremum means either at the point ab has local maxima or local minima. If at the point has local maxima, that time we will get like that, is equal to ab for all xy belongs to open disc center at ab. If local minima, that time we will get greater equal to.
Okay, sir.
Yeah, but those point we can compare like that in some open disc at center point ab. Okay, so here we are getting one open disc. So for all those point the functional value satisfy like that, either like that or this equal to, either less equal to or greater equal to. Okay, one of for all point of neighborhood of ab. But here if you choose one point cd, okay, so you will not get any open disc, you will not get any open disc such that this will satisfy this one, either this one or for all xy belongs to, suppose give the name I. So these two equation never will satisfy, either this one or this one of the inequality will not satisfy. Understood or not?
Yes, sir. Clear.
Yeah, so we'll call those point are saddle point. So this is your local point of local extremum, this point, and we'll call those point are saddle point. Is this clear?
Sir, saddle point.
Yes, S A
Okay,
D
sir.
D L E, saddle point. Okay, so I'm giving the definition. Okay,
Okay, sir.
uh, the same definition, but I'm giving it formally. Okay, let A from D2R have continuous partial derivative f of x and f of y, because for your critical point your this is the condition for critical point, this have to satisfy that this quantity is 0 or this quantity is 0, or at least one of this does not exist. So here we are assuming that have the continuous partial derivative f of x, f of y. Okay, after that let AB be a critical point of f of xy. Okay, so now I am taking one point. So we already know that this is your point of local extrema. So now I am taking one point from here, okay, outside of local extrema. So this will be satisfied like that. The point AB is called saddle point of xy if in every open disc, okay, centered at AB and contain in AB, definitely it should be contained in D. Okay, contained in D, there are points, okay, x1 y1, x2 y2, such that this satisfy, mean we will not get any open disc such that f of AB will be either less equal to or greater equal to of that functional value on that open disc. In every open disc we will get at least 2 points such that this will be satisfied by that function. Okay, we will not get that all less equal to or all greater equal to. We will get that f of x is still less f of AB and still less f of x2 y2. Okay, that time we will call this point is a saddle point. Is it fine?
Yes, sir.
Yeah. So now I am giving how. So till now we get the critical point. So from critical point we are getting two subset. Critical point is union of two subset. One is point of local extrema, one is saddle point. Okay. So
Yes, sir.
we are interested about find the local extrema, but sometimes we are interested about find the saddle point also. Okay, so at first you have to find the what is the critical point. So from full region at first we will find the critical point, then it will be reduced now, then we will get only few points. That time we have to check is it local maxima, local minima or something. Okay, so
Got it, sir.
yeah, so till now from full region we are getting only few points. We have to check now where has the function local maxima, local minima. So there is one theorem, very interesting theorem is there. So finding local maxima, local minima of a function. Okay, before that I am define one thing, Hessian. What is the Hessian? Okay, this is only calculation only for Hessian. Suppose you have one function, define D to R. D is a subset of R2. Okay, means we are talking about only two variable functions. Your Hessian of the function f is determinant of this one, xy f of yy, means f of x is f of yy minus, yeah, this is the your Hessian of a function. Is it fine?
Yes, sir.
Yeah, now we'll go for the main theorem. Yeah, Okay, your main theorem is saying that this is your function. Okay, this is your function, but we will not talk about all arbitrary function, arbitrary two variable function. We will restrict it little bit. Means we will talk about those function have continuous first and second order both partial derivative. Okay, this is our extra assumption for this theorem. So here we are talking about those functions have continuous first and second both order partial derivative in an open disk centered at the point AB. Okay,
Yes, sir.
this is the extra condition. So what is the extra condition? Suppose this is your function f. Let f from D to R have continuous first and second order partial derivatives. So this is our extra assumptions on the function f. Okay, so what are those the first or second order partial derivative? Those are f of x means partial derivative with respect to x, partial derivative with respect to y. Okay, f of xx, f of yy, f of xy. Okay, those are that first and second order partial derivative, and we are assuming all those are continuous. Okay,
Okay, sir.
yeah.
Yes, sir.
Yeah, so and also we are assuming, because we are going for looking for local extrema, so local maxima is a subset of your critical point. Okay, so we are also assuming that the second order partial derivative, okay, where partial derivative will exist in an open disk center at AB belongs to D. So what is this AB? We are looking for only critical point. From full region we are looking for right now only critical point, because already we know that point of local extrema is a subset of critical point. So our aim is to find that local extremum. Okay, so right now we are only looking for the critical point. So this AB are critical point. So this assumption also will take. Suppose AB is a critical point of f of xy. Okay, now we are almost in the end. How we'll find the local extremum point? First one, we'll find this one at first. We'll find Hessian of f at the point AB. This is your Hessian of f. We'll put the value of AB here in xy. Okay, so we'll check what is the sign of Hessian. Okay, here we are assuming that suppose this is greater than 0. Suppose, so maybe there is three condition is there. Hessian may be positive, maybe negative, or maybe 0. So three condition is there. Okay, first condition we are assuming, suppose your Hessian at the point AB is still greater than 0, then we look for the second order partial derivative. Okay, go this one. At first we will look for what is the Hessian at the point AB. If it's positive, then we look for another two condition. If your second order partial derivative f of x's at the point AB is less than 0, then f of xy has a local maxima at AB. Can we connect with this one for your single variable function? For single variable function, at first we used to do first order derivative have to be 0. So here this is nothing but your critical point. Okay, for your two variable functions. Okay.
Yes, sir.
Yeah. So after that we will find the what is the Hessian of the function at the point AB. Okay. So if your Hessian is greater than 0, then we will look for your this quantity. If this quantity less than 0 means if your for single variable function your second derivative at the point is less than 0, we will get the maximum. Here also similarly we are getting local maxima at the point AB. Okay. When your Hessian at the point is greater than 0, this you have to keep in your mind. Second one, what we will get for local minima? So if second order partial derivative with respect to xx is is this should be greater than, okay, greater than 0, then f of xy has a local minimum at AB. It's fine.
Yes, sir.
So at first you have to find the critical point, means f of x equal to you have to 0 and you have to 0 f of y also. Okay, then you have to find the critical point. Then you have to find, suppose you are getting 5-6 point, so fixed at one point AB, then find the Hessian at the point. Check is it positive, negative or 0. If it's positive, go for second partial derivative. If it's negative, then local maximum. If it's,
Hello, sir.
please tell.
Sir, Hessian of f, what does it mean here?
Okay, Hessian is only determinant of this matrix. This
Okay,
quantity.
okay, sir. Okay, ठीक है, sir. Jacobian.
Yes. Yeah.
Okay.
Okay. Yeah. If this quantity is greater than 0, then we will get the local minima. Okay. So another two possibilities maybe is there. Your Hessian at the point may be less than 0. Then what we will get? Suppose second one is, suppose your Hessian at the point AB is less than 0, then what we will get? Then we will get f of xy has a saddle point. Okay. Another condition, another possibility is there also. If this one is 0 at the point AB is 0, then
Neither maxima, neither minima.
yeah, nothing can be said, nothing. Maybe local maxima may exist, may or may not be also. We can't say anything for this one.
Okay,
That
sir.
time we have to check through only graphically. Okay, I'll give one example. Not today is not possible, but next day I'll give one example that Hessian is 0, then I will find the local maxima, local minima. Okay.
Okay, sir.
Yeah. Nothing can be said in general. Yeah. So this is the whole story. Okay. So initially we had full design. Okay. So how we'll find the local maximum, local minima? That time what we did, we found the critical point. Then we will get some few finite points. Okay, maybe we can get many other points also, but for this thing, suppose we will get few points, few critical points. After that, we will check how many points are local maximum, local minimum. That time we have to take one point and you have to find the Hessian of the function at the point. If it's greater than 0, then we have to go for second order partial derivative. Okay, f of x is only. If is less than 0, this is saddle point. If it's greater than, if it's equal to 0, then we can't say anything right now. We have to check, go through for the graphically. Okay. So one thing one can do, one can ask one thing, where we are looking for only f of x, not f of y. Could you please give me the answer of this question? When your Hessian is strictly greater than 0, only we are looking for f of xx, not in f of y. Why? Yeah,
Sir,
look. Please tell. Yeah.
X and Y are independent variable, no? They won't affect each other.
Not like that. Here we are talking about sign only. Okay, now where here we are talking about sign of this quantity at the point AB. Okay, so we can check here when your Hessian is greater than 0, strictly greater than 0. Okay, and so what is the possibility? Suppose this quantity is always this quantity is always positive, at least greater or equal to 0, maybe 0 also, but at least greater or equal to 0. Okay, this quantity is greater or equal to 0. Okay, for positive, this full quantity your have to be positive. Okay, so when this
Yes, sir.
when this quantity will be positive, when these two different quantity have the same sign. Is it or not?
Oh, yes, sir.
Yes, sir.
If suppose one is positive, one is negative, then this whole quantity will be negative, and this is already negative with this non-zero non-negative means your whole quantity will be negative. So when we are assuming that Hessian is strictly greater than 0, that time f of x's and f of y both signs should be the same. Okay, so if one can find that f of x's is enough.
Understood, sir.
Yeah. Okay. Now try one example. One simple. We'll start with simple example. Okay. Yeah.
Sir, in the last, what did you say about that plus minus sign?
Okay. Suppose when your Hessian is positive, is it enough to check the sign of f of xy? That was my question. Why? When your
Sir,
Hessian
they should be of same sign. F of xs and f of y should be of same sign.
should be the same sign, because suppose one is positive, one is negative, this whole quantity will be negative.
Yes, sir. Correct.
Yeah.
After that, sir?
Yes, this is your non-negative quantity, so whole quantity will be negative. Okay, is it clear?
Yes, sir.
Yeah. So now we are going for one example, simple example. Okay, find the extreme value of f of xy is given by, I'm writing here. Okay, xy minus x square minus y square minus 2x minus 2y plus 4. Okay, so you have to find the extreme value, maybe local, maybe global. Okay, and one thing I forgot to mention, that your I think I mentioned that your local maxima, local minima, this you have to find for only interior point. When we will go for global or absolute, means that time we have to go for boundary as well as boundary also. Okay, suppose you have local global or absolute maxima in your interior, that time one of the local maxima will be same of that. Okay, Is it clear or not? Please tell me at first. For local maxima, local minima, we have to find for interior point only. Okay, because it is depend on one neighborhood of that point.
Yes, sir.
And for absolute extrema, it may be in interior, it may be on boundary also. Okay, if it is in interior, that time definitely it will equal to some local maxima. Okay, definitely from the definition only.
Sir,
Please tell.
local maxima cannot lie at the boundary point.
Yes, yes, yes.
If it lies, then it will become absolute.
No, it can't lie. Local, because local maximum, local minimum only depend on neighborhood of that point, not in
Okay,
the
okay, sir.
whole region. Okay.
Sir, because at the extreme we can't define the limit from the both end if it
Yes,
lies at the
yes,
boundary.
yes, yes, yes. Yeah, we can, because for your local maxima, we will look for neighborhood, and neighborhood should be contained in the region. If you take a boundary point, na, so we can draw one neighborhood around that point. Okay, which will contain a region. This is the main issue for local maxima, local minima. So for local maxima, local minima, it should be an interior point. Okay. Okay. So what is the domain for this one? Take the full R2. Here I am not restricting anything. So domain of F is your whole R2. So you have to find the extremum value. Okay, point of extremum on R2 only. Okay, so that time you have to check that all partial, all means at least first or second order partial derivative are continuous or not. We can check, because this is your nothing but a polynomial of two variable. Okay, so all partial derivative are continuous, exist as continuous. So the condition of your this theorem is satisfied, that your first or second order partial derivative have to continuous. So this condition is satisfied. Then you have to find, what you have to find? Critical point. Is it or not? You have full region. From there you have to find only critical point. That after that we can check that theorem. Okay. So for critical point, this should be, these two quantities should be 0. Okay. So what is your f of x? F of x is nothing but what? Y minus 2x minus 2. Okay. Is it? This should be 0. F of y, x minus 2y minus 2 should be 0. If you calculate these things, we will get x equal to y equal to minus 2. Please tell me, is it correct or not? It's fine.
So this for critical point,
Yeah, for
okay,
critical point,
first derivative, partial derivative should be 0.
0. Yes. Partial derivative with respect to x and partial derivative with respect to y, both have to be 0. Okay.
Yes, sir.
So from there we will get this one. Means we have only one point only. So from full region R2 we are getting only 1 point. This is the only possibility for local maxima or local minima, and this is your interior point of R2, because in R2 there is no boundary point is there. Okay. Okay. So this is your
Yes, sir.
interior point of R2. You have to check the local maxima, local minima. Okay. So how we can check? Calculate this one. F of x's. What will be the f of x's at the point minus 2 minus 2? This should be only minus 2. Okay. And f of y minus 2 also, this one minus 2. And what is this one? F of xy. What should be? This is only 1. Is it or not? It's fine.
Yes, sir.
what is the Hessian of the point minus 2 minus 2? Is nothing but minus 2 minus 2, 1 and 1, means 4 minus 1 equal to 3 is greater than 0. So at the point minus 2 minus 2, this has the extremum. Okay. So is it maximum minimum? How will check? We have to check this quantity only. This is your minus 2 less than 0, means at the point minus 2 minus 2 it has the local maximum.
Yes, sir.
Okay, it has the local maxima, but there is no other point, no other boundary point is there, no other interior point is there. Okay, so for this case this should be also the your absolute maxima also. Okay, is it fine or not?
Yes, sir.
Yeah,
So this f of x,
please tell.
matlab it is negative, so we are getting the local maxima here.
Yeah, local maxima is fine. So at the point this one, so I am writing this one at minus 2 minus 2, f has local maxima. My question is this point is local absolute maxima or not?
No, because endpoints are not included, no?
So yeah, this is the question. So here in R2 no boundary is there. Is by definition no boundary is there, na? So only you have to look for interior point. Since no boundary is there, we can't do anything. If boundary is there, then that time we will find. Okay. So in R2 no
Sir,
boundary.
it should be the absolute maximum if there are no any other points.
Yes. Yes. Suppose
If there is only one, then it is absolute.
yes. Yes. I agree. Yeah, this is your interior point. No boundary point is there in R2. This is only interior point, and only one point is in this one point is local maximum is this one. So this have to satisfy always. This greater equal to f of xy for all xy belongs to R2. This have to satisfy always, and this quantity is your 8. So this point also is your absolute maxima. Okay, f has absolute maximum. Okay, because understood or not, please tell me. In R2 no,
Sir, understood.
yeah, no boundary point is
Yes, sir.
there. Okay.
If the domain has only one element, the local maxima and the absolute will be same.
Yes, 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 yes. I agree. Yes. So I'm giving you another one. This is, yeah. Please do it by yourself. I'm giving one example. Okay. This is also not that much difficult. Investigate f of xy is given by x power 4 y power 4 minus 4xy plus 1 for ex extreme value. Investigate this one. Please tell me. Yeah, at first find domain. Take domain is R2. Okay. Domain of f is equal to your R2. Yeah. Now please tell me and check that first order, second order partial derivative of contrast, because this is also one polynomial. Okay, in xy. Okay, so all first order, second order all are contrast. So your condition of theorem is satisfied. Now find the critical point. This is your first goal. For critical point, what you have to do? For critical point, please tell. What you have to
Sir,
do?
fxx and fyy.
0. Please tell me what is that?
Oh, so 0, 0 will be there. No?
What is your coming? F of x. What you are getting for f of x?
Sir,
You are
4x
getting
cube minus 4y.
for x cube minus
4y.
4y. So it should be 0. So here we are getting x cube equal to y. Is it?
Yes, sir.
Similarly, we will get 4y4 minus y cube minus 4x
4x.
equal to 0 imply we are getting
Y cube is equals to x.
Equals to x.
x. Okay. Now put the value of y here. So what we will get? x9 equal to x.
So x power 8 equals to 1. X equals to
No, 1
1.
minute, 1 minute. X power 8, how we can tell? We can tell like that. X into this one. You can cancel the x, na? So this one, this possibility is there.
Ah, yes, sir. X equal to 0 will be there also.
Yes. So from here we are looking for DL only because R2 is there, na? So
Okay, 0, 1.
1 minus 1 also.
Yes, sir. Minus 1.
Yeah. So parallelly what we will get for y also we will get like that. For 0 corresponding 0, 1 corresponding 1, minus 1 corresponding minus 1. You can check it. When you put here x equal to 0, we will get y equal to 0. Okay, here from here. Put x equal to 1, what will get? Y equal to 1. Put x equal to minus 1, we will get y equal to minus 1 from this equation. So this we are getting only 3 points. One is 0, 0, one is 1, 1, another is 1 minus 1. This one. So you have to check now. Now this is little bit, not that much, but little bit calculative. You have to check for 3 cases at the point 0, 0. You have to find Hessian. Okay. So what is this quantity? Please tell me. So before that you have to find f of xx here. Okay.
Yes, sir. 2.
Yeah.
12x square, f of xx.
So what you are
Therefore,
getting
y
as
also
Hessian?
12 by.
Please tell what is this quantity f of xx is
12x square.
12x squared. So at the point 0, 0 is 0. Okay. Is it? Yes. And f of y at the point 0, 0 is also 0. These two quantities we are getting 0. Okay.
Okay.
So f of xy we are getting minus 4 only. Okay. Minus 4, minus 4. So we are getting, what we are getting? Minus 16. Is
Sir,
it?
negative Hessian.
Yes. So this is your 0, 0 is your saddle point. Okay. 0, 0 is a saddle point.
Ah, yes, sir. Minus 16. Okay.
Yes, Hessian is negative. So 0, 0 is saddle point. Okay. Now go for at the point 1, 1. Please tell me what is your Hessian. F of xy at the point 1, 1 is 12 only. Okay. This is also 12. This is 4. This is 4. So this quantity will be positive. Okay. Is it correct?
Yes, sir.
Yes. So now check this quantity. F of x's at the point 1, 1 is 12. Sorry, not 12. This is minus 4, I think, na? Minus 4 or some, what is this? It's 12, 12.
12, sir.
Yes. So this is positive, means local
Minima.
Local minima.
1 1. And what is the functional value at the point 1 1? Is, put the value here. So we will get 1 1 2 3 minus 4. Okay, means minus 1. This is your minus 1. Okay, and at the point minus 1 minus 1, what we will get? Hessian of what we will get? We will get here 12 x square, means this is also positive. Okay,
Sir, it will be same now.
yes, same. We will get 12 minus 4 also positive. And what is this quantity?
Local minima, sir.
What will be this one? Is also 12. Okay, positive. So what we are getting? Local
minima.
at the point
Minus 1 minus.
minus 1. What is the functional value at the point minus 1 minus 1? Same na, because this is your even power.
Oh, yes,
Even
sir.
power.
Yes, sir.
Yes, so this is your also minus 1. So this is also your absolute minimum also. This one minus 1. Is it or not?
Yes, sir. Yes.
Yes, sir.
Yeah,
Local
this is also,
minimum.
both are absolute minimum. Okay.
So, sir, there is no local maxima here.
No local maxima is here. This is the interesting, na. We have 3 point. One is saddle point, and both 2 point are local minima is
minima.
there, and value of the local minima both are same. So both point are absolute minima also. Okay.
Okay.
Suppose
So, sir, here absolute minima. What can we say about absolute minima here?
minus 1 means both point have the absolute minima. Both point means 1 1 and minus 1 minus 1. At the both point, this function has the absolute minima also. Okay. Understood? or
Yes,
not?
sir. Correct.
Yeah, because
Correct.
for both cases we are getting minus 1. Now suppose if you get one is minus 1, one is minus 2, that time you can say that minus 2 is the absolute minimum. But both cases we are getting minus 1. So minus 1 is the absolute minimum. So both are the absolute, both cases we are getting the absolute minimum. Okay.
Sir, if local minima would vary in one case, then what can we say about absolute there?
If suppose we are getting minus 1 minus 2, okay, at two different point, that time minus 2 will be your absolute minimum. Is it or not?
Means like a critical point, absolute will be also lie on the critical point itself.
No, if no boundary is there, only that time. So in both cases no boundary is there. Next we'll go one next example. That time you can observe the boundary is there. That time scenario will be little bit different.
Okay, sir, got
Yeah.
it. Proceed, sir.
For if only interior point is there, okay, so we'll find all local maxima, local minima. Among them we can choose the which is the absolute, which is the absolute maximum, and which is the local absolute minima. Okay, suppose in 2 point local maxima is there and value is 2 and 3. 3 will be the absolute maxima. Is it or not? For the interior point only. If there is no boundary point, only that time. Okay. Now I am giving one exercise for your home, because
Also, sir, this function is not a injective function.
Here, yes, because in 1 1 and minus 1 1 we are getting both same value. It's not injective function.
Okay, sir.
Yeah. So I'm right now I am giving one example. There your boundary will be there. Okay. Yeah. This will in the previous two cases no boundary was there. Only interior point is there. Now I am giving you one exercise. Okay, so two plus 2x plus 2y minus x square minus y. So this is your functions. Okay, and here I am giving you the domain. Define on the rectangular region, okay, bounded by the straight lines, this three straight lines there, y x equal to 0, y equal to 0, and x plus y equal to 9. Here I am giving you one region where boundary point is also there. Okay, so what will be your region? X equal to 0 means this line, y equal to 0 means this line, and x plus y equal to 9 means your this line. Okay, this is your x plus y equal to 9 lines. Okay, so in this region you have to find the what is the absolute maxima and absolute minima. Here boundary is there, this is the boundaries. Okay, you have to check on boundaries also right now. From theorem we can use for interior point only. Okay, but in boundary point we can use that theorem. Okay, so you have to find the local absolute maxima, absolute minima. You have to check that at first you have to check the local maximum, local minimum, interior point. After that we have to check on boundaries also. Then you have to compare. After that you have to decide which one is absolute maximum and which one is absolute minimum. Understood or not? Please tell me. Is it clear?
Yes, sir.
Oh, yes, sir, clear.
Okay, so today you want to solve this problem or next day? Please tell me. If you want to solve today, then I'll do. You want to solve today?
Sir, first we will work out.
Now, what do you want? If you want, then I'll give you to exercise. And if you tell that you want to do right now,
Sir, as an exercise.
okay, I am giving the hints. Okay, so at first, as usual, find the for interior point. Okay, how previous to example we done. So please do similar things for interior point. Now we have to check for boundary point. There is no theorem. This theorem is only satisfied for your interior point. Okay, already I told. Yeah, this theorem is your AB is from your AB is the interior point. Okay, okay, and also critical point also. Okay, so now you have to check for boundaries. Okay, how you will check for boundaries? So this is your total corner point 0 0 9 comma 0. You have to check the functional value at this corner also. Okay, at first check for interior point, write down, go for corner point and write the value of that point also. Then go for one by one, take this A point, this B point, C point. So on AB, what is the equation for F? Here is 1 y equal to 0. Okay, So you are getting f of x comma 0 is 2 plus y is 0 means this two will be cancelled, 2 plus 2x minus x square. Now it is become a single variable function. So you know how to find the maximum minimum for single variable. Okay, find that point. So here already y is 0. Suppose you are getting one point, suppose a. So your point will be a comma 0. Okay, is it or not? Please tell me.
Yes, sir.
Okay, it's on AB. Go for AC. On AC your x is this one, your x is 0. Okay, so what you will get? You will get f of 0 comma y. It will be 2y minus a square. From here also you will get some b, and that time your point will be 0b. Okay, check the extremum. Check extremum. Okay, extreme value for this case also.
And sir, along the line, that hypotenuse line,
Yes, on
basic.
your BC. On BC, what is this? This is given by x plus y equal to 9. So imply y equal, put the value of this one, y or x, whatever. So you will get x comma 9 minus x. So write down the equation. You will get some simplified equation. This is also single variable function. You know the formula how to find the a maximum minima. Is it or not? So from here also you will get some point. Suppose you are getting x is a, what will be y? 9 minus a. Okay, is it fine?
Yes, sir.
Yes, sir, fine.
Yeah, then check all the point and decide what is the local, which is mini, what is the local maxima, local minima, and check the absolute also. Okay, yeah, try to solve in home, then we will discuss in next class. Okay,
Okay, sir.
yeah. Do you have any question?
Thank you, sir. Sir, a previous class notes is there now on the portal.
No, I did not upload it. I have to upload it.